Okay, welcome to review lecture 7.1b, Induced EMF, which is part 2 of 2 parts. If you have not yet reviewed lecture 7-1a, Induced EMF part 1, please do so now or you might not know what we're talking about. Now this is physics for Physics 222 students, which is calculus-based. If you are a non-calculus-based student, please go ahead one slide to slide number 4. Okay, an EMF is induced by a changing magnetic flux, even if the loop through which the flux is changing is not a physical conductor but an imaginary line. The changing magnetic field induces an electric field E at every point of such a loop. The induced EMF is related to E by the EMF equals the integral of V dot ds. Using the induced electric field, we can write Faraday's law in its most general form as the integral of V dot ds equals minus n d phi b dt. And this says that a changing magnetic field produces an electric field. Induced electric fields are produced by a changing magnetic flux, not by static charges. Since induced electric fields are closed loop, electric potential has no meaning for induced electric fields. But this is the first step toward electromagnetic radiation. Now, if you're a Physics 222 student, at this point you should skip ahead to slide 5. If you are a Physics 122 student that is non-calculus based, we should be on slide 4. That's right here. An EMF is induced by a changing magnetic flux, even if the loop through which the flux is changing is not a physical conductor, but an imaginary line. The changing magnetic field induces an electric field E at every point of such a loop. The induced EMF is related to E by the EMF equals the integral V dot ds, or approximately equals the sum over the whole loop of E cosine theta delta S. Using the induced electric field, we can rewrite Faraday's law in its most general form as, and of course this is for Physics 222 students, but it doesn't hurt anybody to see this. The integral of E dot ds equals minus n d phi b dt. We can approximate this as the sum of E cosine theta delta S is approximately equal to minus n times delta phi b delta t. A changing magnetic field produces an electric field. Induced electric fields are produced by a changing magnetic flux, not by static charges. Since induced electric fields are closed loop, electric potential has no meaning for induced electric fields. But this is the first step toward electromagnetic radiation. Now, if you are a Physics 122 student, you should go ahead to slide number 11. If you are a Physics 222 student, you should be on slide number 5. Okay, so now we're going to calculate the induced electric field to a changing magnetic field. We're going to do this inside and outside of this circular region of magnetic field. Now, the magnetic field is within this yellow region here, within this area here, and it's pointing into the page. And we're going to take a circular path around the center of this in 2 places, right here, inside this yellow part where the magnetic field is, and outside the magnetic field. So we have a changing magnetic field as shown below, assuming that big R, which is this radius of the magnetic field influence area, is 8.5 centimeters, and the time rate of change in the magnetic field is 0.13 Tesla per second. Find an expression for the magnitude E of the induced electric field at points within the magnetic field and radius little r from the center of the magnetic field, and then we're going to evaluate that expression for R1 equals 5.2 centimeters. We're also going to find an expression from the magnitude E of the induced electric field at points that are outside the magnetic field and radius r from the center of the magnetic field. We're going to evaluate this expression for R2 equals 12.5 centimeters. The physics of this is pure Faraday's law. So we write down the knowns and unknowns. Big R is 8.5 centimeters, that's 0.085 meters. dB dt is 0.13 Tesla per second. R1 is 0.052 meters. R2 equals 12.5 centimeters or 0.125 meters. We want to know the electric field. And we know that the EMF equals the integral V dot ds, and that has to equal d phi b dt. Now, we don't need n because we only have one loop. Okay, so ds is then r d theta, and phi b is b times a, and the area, of course, is pi r squared for when we're inside the magnetic field, that is little r less than big R, or pi big R squared for little r greater than or equal to big R. Okay, so now we're going to split this up into 2 solutions. One is inside the yellow circle here. The other is outside the magnetic field, so outside this yellow circle. So the inside first, the integral V dot ds equals d phi b dt. So we can pull the E out because the E is constant along this loop. So E times the integral of ds is E times the integral of r d theta. That has to equal area times dB dt. Of course, this area B is just phi b. The area doesn't change, only dB dt is changing. So then we know that the integral is E times 2 pi r. This comes from the circumference of the circle. And the area, of course, is pi r squared dB dt. And this is for inside this yellow area. So that E then, the expression for E is r over 2 dB dt. And this is for little r less than big R. So in other words, inside this yellow magnetic field here. Okay, now for the outside, the area outside the magnetic field, where little r is greater than or equal to big R, we still have Faraday's law. The integral of E dot ds equals d phi b dt. We can pull the E out because it's constant along the loop here. So E times the integral of ds is E times the integral of r d theta, and that has to equal a dB dt. So then we know that the integral, that this expression evaluates as E times 2 pi r, where this is the circumference, and that equals pi times big R squared, which that's the area, dB dt. So E, when you're outside this yellow area here, outside the magnetic field, E equals big R squared over 2 times little r times dB dt. Okay, so now let's stick the numbers in. Okay, this is we're looking for the little r equals 0.052 meters, which will be in here. So we have this expression, and now we're going to put the numbers in. So E equals 0.052, that's little r divided by 2, and dB dt is 0.13 Tesla per second. Turns out that the EMF in this area at 0.052 meters from the center is 0.0034 volts per meter. Now we're going to get it at r equals 0.125 meters, which is outside the magnetic field. And we had an expression on the previous page, which is just right here, and now we can plug the numbers in it. E equals the big R squared of 0.085 meters, and we're going to square that, divided by 2 times 0.125 meters, that's the little r. dB dt is 0.13 Tesla per second. So the EMF is 0.0038 volts per meter. Now this says that a changing magnetic field creates an electric field, and you don't even need the conductor. The electric field is created in empty space, even if no conductor is present. And again, we're heading toward the second half of the course, which is electromagnetic radiation. Okay, if you are a Physics 222 student, you should be here. If you're a Physics 122 student, you should be on slide 11. So, calculus-based. The axis of a coil of 250 turns in area 0.0020 square meters is aligned at 40 degrees to a uniform magnetic field. Magnetic field is decreased from 0.080 to 0.020 Tesla in 0.020 seconds. What is the average EMF generated in the coil? If the resistance is 24 ohms, what's the average current? Write down the nodes. The N is 250 turns. The area is 0.0020 square meters. B1 is 0.080 Tesla. B2 is 0.020 Tesla. The change in magnetic field is just the subtraction of those two, which is 0.060 Tesla. Again, we only care about the magnitude. And the time lapse is 0.020 seconds, and theta equals 40 degrees. The physics of this is Faraday's law. Phi b equals AB cosine theta, and the EMF is minus n d phi b dt, and that has to equal minus n times A times the cosine of theta dB dt, because only the magnitude of the magnetic field is changing, not the area of the coil. So now we can stick numbers in. We have the EMF is 250 times 0.0020 meters, this is units conversion, times 0.060 Tesla divided by 0.020 seconds. It is 1.15 volts. The current is just that EMF divided by 24 ohms, or 0.048 amps. So 48 milliamps and 1.15 volts. Okay, if you're a Physics 222 student, skip ahead to slide number 13. If you are an algebra-based student, 122, slide number 11. The axis of a coil of 250 turns in area 0.0020 square meters is aligned at 40 degrees to a uniform magnetic field. Magnetic field is decreased from 0.080 to 0.020 Tesla in 0.020 seconds. Okay, what is the average EMF generated in the coil? If the resistance is 24 ohms, what's the average current? We write down our nodes. N equals 250. Area is 0.0020 meters squared. B1 is 0.080 Tesla. B2 is 0.020 Tesla. The change in magnetic field is just a subtraction of those two, and it's 0.060 Tesla. Again, we only care about the magnitude here. The time lapse is delta t is 0.020 seconds, and theta is 40 degrees. Physics of this is the Faraday's law. Formula equals phi b equals AB cosine theta. The EMF is minus n delta theta b divided by delta t, or minus NA cosine theta delta b delta t, since only the magnitude of the magnetic field is changing, not the area of the coil. The numbers now we can put in the numbers, and the EMF is 250 turns times 0.0020 square meters for the area. This is units conversion, and the change in magnetic field is 0.060 Tesla, and it's occurring in 0.020 seconds. It is 1.15 volts. The current is just the EMF over R, or 1.15 volts divided by 24 ohms, or 0.048 amps. So 48 milliamps and 1.15 volts. If you're a Physics 222 student, you should be on slide number 13. If you're a Physics 122 student, please skip ahead to slide number 15. Okay, in the figure, a long rectangular conducting loop of width L, resistance R, and mass M is hung on a uniform magnetic field B that is directed into the page and exists only above this line. So in other words, the magnetic field is only above here. Okay, the loop is dropped. During its fall, it reaches a certain constant velocity Vt. Ignoring air drag, find Vt. Assume the loop reaches Vt before it falls completely out of the field. Okay, in this case, we're just going to drive an expression. So the knowns are L, R, which is the resistance of the loop, the mass of the loop, magnetic field B, G, and N, which is one loop. Theta is 90 degrees, and that theta is the angle between the magnetic field and this L. Vt, of course, was what we're looking for. The physics of this is Faraday's and Ohm's law, Newton's law of force on a wire in a magnetic field. The formula is Fm equals IBL. That's just dragging this wire through the magnetic field. Fg equals m times g. Summation F equals ma has to equal 0 because it's reached constant velocity and acceleration is 0. So E over R equals I, and the EMF equals n d phi b dt. Phi b is, of course, equal to BA cosine theta. A is L times Y, where Y is the distance between the top of the loop and the edge of the field at the cutoff point. We solve this. dA equals L dy. Phi b equals B times A. Fm equals IBL. That is equal Fg, which equals mg. Put this together, we end up with E over R equals I equals mg divided by BL. Okay, so at this point, we've gotten to here. And we can say that d phi b dt equals b times dA dt. That is equal BL dy dt. Bt, of course, is dy dt. So the EMF is n d phi b dt. And that is equal n times b times L dy dt. N times b times L times Vt. And that is equal R times m times g divided by BL. So the solution of this is Vt equals mgr divided by the quantity BL squared. Now, if you're a Physics 222 student, please skip ahead to slide number 17. If you're a Physics 122 student, you should be on slide 15. Okay, so here's an example. In the figure, a long rectangular conducting loop of width L, resistance R, and mass M is hung on a uniform magnetic field B that is directed into the page and exists only above this cutoff line AA prime. The loop is dropped. During its fall, it reaches a certain constant velocity Vt. Ignoring air drag, find Vt. Assume the loop reaches Vt before it falls completely out of the magnetic field. Okay, now we're going to drive an expression here. The knowns are L, R, M, B, G, and of course we have one loop for N, and theta is 90 degrees, because theta is the angle between this L and the magnetic field. We're looking for Vt. Physics of this is Faraday's and Ohm's laws, Newton's law of force on a wire in a magnetic field. The formula is Fm equals IBL, Fg equals mg, summation F equals ma has to equal 0 because it's reached constant velocity and acceleration is 0. The EMF over R equals I, and EMF equals n delta phi b delta t. Phi b equals BA cosine theta, A equals L times Y, where Y is the distance between the top of the loop and the cutoff at AA. Now we put all of this together. Delta A equals L delta Y. phi B equals BA, FM equals I, BL equals FG equals MG. So then we can say that E over R equals I. That has to equal mg divided by BL. Okay, so that's what we got to right here. So now delta phi B delta T is just B times delta A delta T. And that's because the magnetic field itself isn't changing, the area, the amount of area enclosed by the loop is changing. So now we can say delta phi B delta T is equal to BL delta Y delta T. And we know that VT equals delta Y delta T. So then the EMF is N times delta phi B delta T. So that equals NBL delta Y delta T. And that has to equal NBL VT, which equals RMG divided by BL. We can solve this for VT. VT equals MGR divided by the quantity BL squared. Okay, so a wire loop is being pulled through a uniform magnetic field. What is the direction of the induced current? There is no induced current. It's not leaving the field. The magnetic field is uniform. The loop is not shrinking. It's just going off to the side. As long as the loop stays in the magnetic field doesn't change, there is no induced current. A wire loop is being pulled through a uniform magnetic field that suddenly ends. What's the direction of the induced current? And what happens when the loop is completely out of field? Well, I can tell you what happens when the loop is completely out of field. The EMF and the current will drop to zero once the loop exits the field. Now for here, this first part of this, it's clockwise. The magnetic field is into the page and it's disappearing in the loop. So in other words, the loop is losing that into the page magnetic field. So the loop will compensate by an induced flux that is also into the page to try to keep this from disappearing. Right-hand rule, thumb is into the page, fingers curl clockwise. The induced EMF and current is in the clockwise direction of the loop. What is the direction of the induced current if the magnetic field suddenly increases while the loop is in the region? What happens if the loop stops moving when it's in the increasing field? There's not going to be any difference between this and that. So basically it would be the same question. Okay, so it's going to be counterclockwise. The increasing magnetic field in the page must be countered by an induced flux out of the page. There's a right-hand rule. So thumb is outward, fingers curl counterclockwise, so the induced EMF and the current is in the counterclockwise direction in the wire loop. If the loop stops moving while it's in the increasing magnetic field, there's an induced EMF and current in the counterclockwise direction. This will continue as long as the magnetic field is increasing and the loop does not leave the magnetic field. So the answer to these two questions is the same. Okay, wire number 1 of length L forms a 1-turn loop and a bar magnet is dropped through it. Wire number 2 of length 2L forms a 2-turn loop and the same magnet is dropped through. Compare the magnitude of the induced voltages in these two cases. These 222 students, calculus based. If you're non-calculus based, please skip ahead a slide. Okay, so the correct answer to this is number 2, where V1 is less than V2. Faraday's law says that the EMF is proportional to the number of turns, that's the number of loops. So the induced EMF is twice as large in the wire with the 2 loops, wire with the 2 loops is with the one with the 1 loop. Okay, if you're a Physics 222 student, please skip ahead to slide number 26. If you're a 122 student, that is algebra based, this is slide number 25. Okay, so what's going to happen is V1 is going to be less than V2. Faraday's law says that the EMF is proportional to the number of turns, number of loops. So the induced EMF is twice as large in this one as it is with that one. Okay, wire number 1, same question pretty much. Length L forms a 1-turn loop and bar magnets drop through. Wire number 2, length 2L forms a 2-turn loop and the same magnets drop through. Compare the magnitude of the induced currents in these two cases, assuming Ohm's law applies to wire. Resistance equals rho L over A. Well, Faraday's law says that the EMF is proportional to the number of turns in the loops. Okay, so the induced EMF is twice as large in the wire with the 2 loops as it is in the wire with 1 loop. The current is given by Ohm's law, I equals V over R. But wire 2 is twice as long as wire 1, so it has twice the resistance. So these two effects are going to cancel out. So they're going to wind up with the same current, but it's not equal to 0. A bar magnet is held above the floor and dropped. In number 1, there is nothing between the magnet and the floor. In number 2, the magnet falls through a copper loop. How will the magnet in case 2 compare to the magnet in case 1? Okay, so what's going to happen is number 2 will fall slower. When the magnet is falling from above the loop in number 2, the induced current will produce a north pole on top of the loop, which will repel the magnet. When the magnet is below the loop, the induced current will produce a north pole on the bottom of the loop, which attracts the south pole on the top. and the current will reverse as the magnet passes through the loop. And what happens when magnets turn so the other pole is toward the floor before it's dropped? Turning the magnet only changes the direction of the induced EMFs and currents in the loop. The magnet will still fall more slowly through the loop. Now, the other way you can think of this is when this thing's falling through the loop, the current in here, the EMF in here is generating a current in this loop, and guess what that's doing to the loop? It's heating it up. So this energy that's being dissipated as infrared heat, infrared radiation, is being stolen from the kinetic energy of this one. So in other words, the gravitational potential energy is the same for both of them, but this one only is converting it to kinetic energy. This one is converting it to kinetic energy and thermal energy. Okay, if there's an induced current, doesn't that cost energy? Where would that energy come from in case 2? In both cases, the magnets are identical and they are dropped from the same height. Well, there's less kinetic energy in case 2. In both cases, the magnet starts with the same initial gravitational potential energy. In case 1, all the gravitational PE is converted into kinetic energy. In case 2, we know the magnet falls slower, so there's less KE. The difference in energy goes into making the induced current and heating the copper wiring. Okay, bar magnet is held above the floor and dropped. In case 1, there's nothing between the magnet floor. In case 2, the magnet falls through a plastic and non-conducting loop. What is it, if anything, is induced in the plastic loop? It's EMF. You do not need a conductor to induce EMF, just a changing magnetic flux. If you do have a conductor, the EMF will also generate a current. A bar magnet is held above the floor and dropped. In case 1, there's nothing between the magnet and the floor. In case 2, the magnet falls through a plastic non-conducting loop. How will the magnet fall in case 2 in comparison to one in case 1? It'll be exactly the same. No current is induced in the non-conducting plastic loop, so there's no loss of kinetic energy. No heating. Okay, a permanent magnet is moved toward a 320-turn solenoid such that the magnetic field inside the solenoid increases from 0 to 0.50 Tesla in 0.75 seconds. The radius of the solenoid is 0.035 meters. The ends of the solenoid are connected in series with a light bulb. What EMF is induced during this time interval? Of course, this is for Physics 222 students. If you're an algebra-based student, please go to the next slide, which is slide number 38. If you're a calculus-based student, you should be here. The EMF is N times A times dB dt. That is 320 pi times 0.035 meters quantity squared times 0.5 Tesla divided by 0.75 seconds. And that is 0.82 volts. If you are a Physics 222 student, please skip ahead to slide number 39. If you are an algebra-based student, please stay here on slide number 38. Okay, so the answer to this is D, which is 0.82 volts. The EMF is going to be N times A dB dt, and that's approximately equal to NA delta B delta T. So 320 pi times 0.035 meters quantity squared times 0.50 Tesla, which is the magnetic field. That's how much it changes in 0.75 seconds. And the answer is 0.82 volts. Okay, conducting rod slides on a conducting track and have a constant magnetic field directed into the page. What's the direction of the induced current? And what's the direction of the magnetic force on the rod? Well, the direction of magnetic force is going to be, it always opposes you. So it's going to be to the left. Okay, so it's going to be counterclockwise. The magnetic field points into the page. The flux is increasing since the area is increasing. Okay, the induced magnetic field opposes this change, so it points out of the page. Right-hand rule, thumb out of the page, fingers curl counterclockwise, which is the same direction as the induced EMF and the current. So what is the direction of magnetic force on the rod? It's to the left, opposite direction of V. An external force is pulling the rod to the right. The magnetic force opposes this, so it's directed to the left. And we can check on this. We have another right-hand rule. We're going to back it up with another right-hand rule. The induced EMF and the current are going up the sliding rod. The index finger is then up the sliding rod. The middle, which is the magnetic finger, is into the page. And if you try this, you'll find out your thumb, which is the fourth finger, points to the left. Now that has to be, because if it didn't, you'd violate energy. You get something for nothing. In other words, you would generate a current, heating up the rod, without having to put any effort in. Thank you.